Hi everyone. Today we will be presenting our project on robust PCA in the context of collaborative filtering. As data scientists, we are accustomed to a data matrix M, which is n by m, where n is the number of observations and m is the number of features. In many situations, this data has properties that make it challenging to process with statistical tools. For example, m may be very large, n may be approximately equal to m, and there may be noise in the data. In these situations, we can use traditional dimensionality reduction techniques like PCA. However, in situations where we have outliers or missing entries in the dataset, we cannot use PCA and we need another technique. In this project, we focus on collaborative filtering. Collaborative filtering is the task of inferring feature values for some subset of your data using populated values. It was made popular by the Netflix prize competition to infer user movie ratings, based on a small number of ratings, by a small number of users which are known. In this project, we describe how the RPCA optimization problem is formulated, and we experiment with RPCA on the Steam video games dataset.
PCA is possibly the most popular dimensionality reduction technique. When posed as a matrix separation problem, we can see that the solution L hat would be the data matrix M in the k principal directions with the largest singular values. This formulation is less popular but will be useful shortly. PCA makes sense when M can be described as the sum of two components, L and N, where L is a low rank component and N captures the noise. But PCA is extremely sensitive to outliers. In fact, even one outlier can skew the results arbitrarily. So if we suspect outliers or corruption are present, then our assumptions about M should change. Thus, if we now assume M has a sparse component S. By finding a good L now intuitively can be pitched as the optimization problem shown. However, this is non-convex as neither of these functions are convex themselves. But we can solve this problem by just doing PCP. Principal component pursuit is a procedure to relax the previous optimization problem, which holds under certain stipulations based on the coherence of M. Intuitively, this manifests as constraints on L and S, and if met, the optimization problem doesn't even have a hyperparameter, as lambda is set to 1 over the square root of the largest dimension, usually n. We find that this convex relaxation is interesting, and we can see how the solution handles the noise, but we found that it was less obvious how this procedure would fill in missing entries as well. To see this, we can realize that matrix completion can be viewed as minimizing the rank of M while filling in M. The optimization problem we show has been proven to exactly solve the matrix completion problem if M meets conditions similar to those of RPCA. In practice, the equality constraint is softened to promote solutions, and we produce an experiment to compare these methods through the lens of collaborative filtering.
So as Jeffrey mentioned, to demonstrate the usefulness and the power of robust PCA, we developed an experiment on the Steam video games dataset to compare this technique to traditional matrix completion techniques. The first step was to actually clean our dataset, and we took a subset of the data to make sure that it was reasonably well populated. Since some of the users had only played one game in the original dataset, and some of the games had only been played by one user. We wanted to make sure that the matrix we were working with was reasonably well populated. So we went with a small data set, 233 by 133, representing users and how many hours they played each respective game. After cleaning the dataset and generating our input matrix M, we saw that there weren't too many outliers in our dataset. There were only a few instances of a user playing a game more than 2,000 hours, and for the most part, users played in the 0 to 100 hour range. So we decided to introduce corruption into our dataset. We introduced values between negative 10,000 and negative 1,000. In this situation, a negative value doesn't make sense. A user can't play a game for a negative amount of time. And we also introduced values between 1,000 and 10,000 to represent the situation where if a user basically dedicates their life to a game, this may not translate well to how long another user might play the game. After incorporating the corruption, we generated various matrices with varying levels of this corruption. So from 0% to 5%, 10%, all the way up to 30% of the populated portion of the data we replaced with corrupt values. And finally, we applied our matrix completion techniques, including nuclear norm minimization and k-nearest neighbors, along with robust PCA on each of these datasets. As you can see, k-nearest neighbors and nuclear norm minimization slightly outperform robust PCA when we have 0% of the dataset that is corrupted. However, as we slowly incorporate corruption into the data, we notice that the error, or in this case, the root mean squared error on the test set, slowly increases for k-nearest neighbors and nuclear norm minimization. And the performance deteriorates significantly as we increase corruption all the way up to 30%. However, the performance of robust PCA remains quite consistent, remaining in the 300 range as we increase the amount of corruption. Here we have some heat maps to help visualize how these different techniques are performing. On the left side, we have our original dataset M with no corruption. And in the middle, we have its low rank component that's extracted by RPCA. And on the right side, we have the sparse component. And we can see certain instances where a user played a game for maybe greater than 5,000 hours. And these are extracted by our sparse component. In the end, L plus S has to equal M, because this is one of the constraints of the RPCA problem. We also can see the heat maps of NNM and k-nearest neighbors. For these techniques, we can see that the original matrix M, some of the missing values are being inferred for some of the games, and it's using the original dataset to infer these values and complete the matrix. The next set of heat maps we have are for the dataset with 10% corruption. As you can see on the left side, we have the original matrix M, but now we have very large values, above 7,500, and very negative values as well. In the center, we see the low rank component, and this is still performing as we would expect it. It's still able to extract some low rank features, and we can see bands representing some of these features. And finally, on the right side, the sparse component is being extracted. And this actually looks quite similar to the original matrix M, because those very large values stand out in the visualization, and we can see those being extracted by the sparse component. Here we can see the heat maps of nuclear norm minimization and k-nearest neighbors in the presence of 10% corruption. As you can see, the matrix completion is still performed. These techniques are still able to infer different values and fill out the matrix, but it's using systematically corrupt data in order to infer these values. So the resulting matrix is itself going to be corrupt. This shows us that robust PCA performs well in the presence of outliers compared to these more traditional techniques.
Finally, we would like to address some subtle details before closing. Firstly, we acknowledge that we didn't focus on the constraints that guarantee that these methods perform well. As mentioned, these constraints are on the outlier sparsity or cardinality and the low rank components properties, but these methods can still be applied even when in violation of these constraints with limited success. Instead, we focus on comparing the performance of these methods to highlight similarities and differences in the algorithms. And note that in practice, matrix completion through nuclear norm minimization is very slow compared to other matrix completion solutions. We also want to note another application of RPCA that we found very interesting, namely video surveillance. In video surveillance, the sparse matrix is actually the target. In this situation, the background image of a surveillance tape would be considered the low rank component, and the changes in the scene are the outliers. We mentioned this just to highlight the versatility of a strategy like RPCA. Lastly, we want to acknowledge some helpful references, namely Data-Driven Science and Engineering textbook, and our professor's notes on matrix factorization, which can be found online. Thank you very much for your time.